Heidi? Oh. Okay. Na gut.
Ist irgendwas noch?
Was ist denn da? Mein Video ist, glaube ich, eingeschaltet, nicht? Und mein.
So, good morning, everyone. Welcome to the Corfu, or to this year's edition of the Corfu workshop on quantum geometry, field theory, and gravity. And welcome to people who are here in Corfu. There is sort of a half-filled audience. I don't know if you can see it online. And welcome also to the people who join us online. So for most of us, this is the first, at least partially, presence meeting after the epidemic, so that's kind of a special thing for everyone. And so it worked very, very well so far, and we are very happy that lots of people joined this workshop. By the way, you're probably wondering where is George Subanos, and that's a very good question. George Subanos is around, but at this morning in this opening, he cannot make it for serious other reasons. So he asked me to take over the opening, which I'm very honored to do. But of course, I cannot really take George's role, so I'm sure that he will find some opportunity to say some extra words to you, which only adds in the way that only he can do it. Nevertheless, let me try just to mention a few things, because, well, most of you have been here before, but maybe not everyone, I'm not sure. Anyway, so this is kind of a rather long tradition. This type of event started, in fact, in 1982. I checked it out yesterday. It started with, there was a series of summer schools, so this the Corfu summer schools on elementary particles or something like that. And that was sort of semi-regularly organized for, I don't know, 20 years or so. And I remember, so I was here for the first time, I think it was 99 or something like that. And already at that time, of course, John Madore was also here, and he was a fixed participant, kind of a fixed point in this series of events. And we will, as you all know, George passed away last August in 2020, and it was an obvious thing for us because he was really a central figure in these events, and most of us knew him very well. So we decided to dedicate this workshop to. I'm not sure. So, was it possible to understand me? Okay, all right. Okay, so as I said, so we decided to dedicate this workshop to the memory of John Madore. There will be several contributions. So Harald Grosse by Maja Buric will say something about his scientific part, but not only his scientific part, of course. And we also have David Madore and Genevieve who join us online. But now the sound.
Yes, I am.
Great. So we're very happy to have you here. And just in 1 second, it would be great if you could say a few words. But before we come to that part, I also have to say a few organizational things. So we had a huge response this time. There was even more participants than the usual here. So which means that we have to reduce the length of all the scientific talks to no more than 30 minutes, which means 25 minutes plus 5. So we have to ask all the participants to really respect this time, because you know the schedule is very long. So we'll in fact sort of make it sort of a ring and alarm sound at 25 minutes, which sort of should tell you to really wrap up the talk. Okay, so that is about the practical aspect of the workshop, and in terms of the really important part today is the memory of John Madore. And also for me, he was a very, very significant figure. He was one of the most approachable figures in this kind of scientific framework, and it helped a lot to people who were young at that time to enter the subject. And he was just, I think we all remember him in very particular ways, in very human ways. But obviously, this should be stated in other words by first of all maybe David Madore. David, can you hear? Would you like to say a few things?
Yeah, thank you. I'd just like to say a few words. First of all, to thank you all for coming. I can't see, but I hear that there are many of you. Thank you all for coming to this workshop, and of course to the organizers for dedicating it to my father's memory. I think it would be very honored As those of you who met him know, and as you just stated, Corfu was a place very dear to his heart, and he very much enjoyed coming here. And there were three things he was particularly fond of, and I think this is the ideal place to do all three. The first, of course, is to do physics, and perhaps even more importantly than doing physics is to share the physics you do. Dad not only liked to do physics, but he enjoyed exposition. And I know this because I was one of his test subjects, if I can say that. And that's how I became interested in science from a very young age. So I hope, well, even though I can't claim to understand any more than just the titles of the talks, the scientific programs here seems very appetizing. And I'd like to thank particularly all the speakers who made it all the way here, or if not in presence, at least online, for sharing your work with the community. The eclecticism of the talks, the wide range of subjects, from cosmology to string theory, I think it perfectly matches the wide gamut of subjects that my father was interested in. So I'm a mathematician, and just to say the truth, my father always saw this as a kind of betrayal. We had our little scientific rivalry between us because I was going into algebra, and he said, p-adics, that's completely uninteresting. And he didn't like to admit that his work was both math and physics, even though it was. And so I'd like to add one personal message here. Don't hesitate to build bridges between mathematics and physics, and to walk across these bridges from one direction to the other, or I mean, one way or the other. So, okay, doing physics was one thing. But the second thing my father was fond of doing, particularly in these kind of workshops, is meeting other people. And just talking to them. And as was just said, he was an approachable figure. And I think, well, first of all, I'm very glad that the meeting can take place in person during or hopefully after at the end of this pandemic, at least for some of you, not just online. So I'm sorry, I would not be able to attend, but it's really nice that you were able to gather. I hope this will be an occasion of many encounters, both scientific, but also just a friendship. I mean, he really liked to talk to people and just chat with anyone. So please do so, and that's one of the great things you can do. And the third thing, of course, was that my dad very much enjoyed to do is enjoy the food, enjoy the drink, and enjoy the place. And Corfu is really a wonderful spot, and I think you can all find this spot very easy. So in summary, share your physics, meet new people, enjoy your stay. That's the best you can do to honor my father's memory. Thanks again for coming, and may you have a wonderful time.
Okay. Thanks a lot, David, for these kind words, and I can relate very well to what you said, and I think most of us can. Now, perhaps Genevieve, I don't know, did you want to say a few words? Or?
Yes, I can. Yes, I may. So, hello, everybody. I'm really deeply moved to be with you today, to remember John during this day in Corfu. So, first of all my thanks to go to George for his firm commitment to fulfilling the promise he made me last year. He would dedicate this workshop to John. So the Corfu conference were for John an eagerly awaited opportunity to meet his friends and colleagues and to discuss and exchange ideas in such a wonderful place and a very friendly atmosphere. So he made a point of participating each year, and even last year in 2020, while already lying in hospital and very in bad shape. He was still hoping he could come once more. So thank you all for remembering him as a friend and keeping his to life. As physicist, thank you. Thank you.
Thank you very much, Genevieve, for being here, and also David for being here and saying these words to us. I think we all appreciate it. And of course, he was also an eminent scientist, and this aspect of his work, I think Harald, Grosse, and Maja Buric will just summarize in the next short contribution. Harald, can you hear me?
Yes, I can hear you. Do you hear me?
Great. Excuse me? I didn't understand the last.
Does it work? Yes.
Yes. Sorry, I'm a bit slow at the moment. But anyway, so the connection works, and I think it's best if you just go ahead, Karabali.
Okay, thank you very much. Welcome, Genevieve, David, and all the others. I'm an old friend of my dear John. I met him first in 1991. That was just at the period where he did really two great things. In 88 and 91, these are the major steps. He created a subject which is still alive. So he contributed over many, many years to a subject which he himself created. Now, my remarks, and thanks also to George and the other organizer to dedicate this workshop to the memory of my dear friend John. Now, my first remarks are on the early years, the years up to 88. In 88, as I said already, he did a very big step together with two colleagues, which we can summarize it from geometry to non-commutative geometry. And what he did, he used matrix geometry to apply for particle physics. I agree completely with David that one should we are using mathematics all time, actually, heavy mathematics, more and more over the years, and apply it to the particle physics and things like that, to classify multiplets, for instance, and so on. And the second big step can be said space-time geometry, space-time non-commutative geometry, actually, which he did alone in 91, and it's called fuzzy sphere. It's well known to everybody. It's the simplest non-commutative space. And I say a few memories at the end. So John was born in Saskatoon. As he always told to me, nobody knows this town. Anyway, and he studied in Toronto. At the time, Coxeter gave lectures. It seems he heard Coxeter, probably. Then he went to France, and soon later he stayed 63, 64 in Hamburg with Harry Lehmann, a well-known quantum field theorist. And we spoke about him, so that's for sure he interacted with Harry Lehmann. He went back to France, where Papandreou, a Greece well-known gravitational physicist, stayed and worked on gravitational waves, a very well-known subject nowadays since they are measured. So that's a big step, of course. And then he went back and forth from Orsay to Marseille to Brandeis, Toronto, Polytechnique, École Polytechnique, and finally settled in Orsay. And if you look now to the subjects which he treated during this kind of 16 years or so, it's enormous how many subjects he contributed. You know, you have to learn a subject, but you should contribute. And John was able to enter the subjects and to contribute. From the gravitational waves to the neutrinos in GR, always classical gravity. Young-Mills fields, monopoles, sigma models. So a broad range of geometric methods were used already by John at the beginning. Einstein, Young-Mills, and Radita-Schwinger field, Kaluza-Klein mechanism, which he always liked very much and compared to non-geometric methods. Lux pairs, twistors, conservation laws, Friedman universe, cosmology, well established subject nowadays and well on the focus, and spin and so on and so forth. So a broad range, and John published on all these subjects. So I think not many people can say this in such a short period. Now in '88, as I said, he joined Michel Dubois-Violet and Richard Kerner, both from Paris. And the three made a very, very big step. They jumped from, if you like to say, Riemannian geometry or Euclidean geometry to non-commutative geometry. And I will say a few words why that is really fascinating. In '91, I learned from John and was fascinated. That was in Marseille. John was not so often in Marseille, so I didn't meet him so often. I actually was invited by Genevieve and John and met the young boy. Now, and they applied it to electroweak models. So the classifications, the W and the Z can be classified as multiplets of a representation of SU2 cross U1, as we know. But that comes out with a Higgs effect involved. But that comes out from a non-commutative geometry. And that has been observed by these three people. So in summary, they developed what is called metrics, the differential geometry of matrix algebras, non-commutative of differential geometry. Now in '91, as I said, John created the fuzzy sphere. I will say a little bit more later. Now, what it means is the subject which John worked so heavily and created from zero, so to say, is to join two pillars on which our fundamental physics relies. That's quantum field theory on the one hand and classical gravity. And in both, there are singularities, there are problems, which mathematicians wouldn't accept. We sometimes hide them. They run under the name of UV, IR, ultraviolet, infrared divergences, the Landau problem, the convergence problem of divergent expansions. And we hope to take gravity into account and to improve on this. And partly it's done. And on the other hand, classical gravity has problems if the time evolution evolves and the black hole forms, time evolution is gone, finished. So that's so to say the end of the story, and we have to improve. We have to change the physics. In terms, it's not renormalizable. So both have problems, and to merge GR with quantum field theory through non-commutative geometry is, so to say, the main goal of what John followed from the side of the geometry side, and some people like me from the other side. So we like to join. Now that space-time is limited by a tiny distance, which is called the Planck length, I mean, by the Planck units, so to say. We all heard from John Archibald Wheeler years before this, but to build a model where this is built in, the fuzzy sphere, for instance, that's really a big step. In 1991, John did it. Also, it sounds very simple, but I hope nevertheless you will appreciate. And we used it to regularize quantum field theory. So what does it mean? We typically start with a partition function like this one here. And S is an action, and J allows to generate correlation functions. So the action, what does the action need? It needs an integration, as you see here. It needs a section of a bundle, which is a field, which means an element of a module. It needs a differential calculus to have gradients and Laplacians and so on, kinetics. And all that can be built in if you go from functions over a manifold to matrices. I liked it enormously. In '91, John explained to me, why do we have to have an algebra which is commutative? Go to a non-commutative algebra. You can have a differential calculus. You have sections of your modules, which are the fields. You have an integration, which is a trace. So you can build and the measure to integrate over all degrees of freedom, which is always ugly in our case and needs regularization, is regularized in the matrix case, as you will see immediately. Oops. So a very simple two-dimensional Euclidean field theory can be built by without any difficulties and divergences and so on, but by using the fuzzy sphere of John. What you do is you start with, as you do, the simple non-commutative algebra, Lie algebra, generators fulfill a bracket of two generators is given by the third proportional to the third generator. So you have gotten three generators, xn, and m and p runs from 1 to 3, and big N denotes the representation, which is integer. So it's 1, 2, 3, 4, and so on in an integer. And 2 times 2 or 3 times 3 matrices, of course, close under the Dirac bracket. Now, John rescaled everything in such a way that the Casimir, which is the sum of the squares of the 3, which means the sphere, x1 square plus x2 square plus x3 square is equal to r square in dimension, if it's of dimension n. So that is a sphere which doesn't have points. This algebra doesn't have any points. So as you will see immediately, you regularize the functions over the sphere in such a way that you have finite degrees of freedom and you preserve the symmetry. Now, correlation functions are given by this measure integrating over all degrees of freedom. And what is the action? As we said before, the integration is a trace. The gradient is a Dirac bracket with the generators themselves. That's a derivation on the algebra. And everything is well defined and nice. So that's a beautiful story. You have introduced a cutoff, which for large n is just r over n. And regularized everything, and you can work with a model without these ugly difficulties which are all times around. And many people like this. That was a boom. You can go to more complicated models to higher dimensions and so. And Harald, our chairman, actually uses such a thing recently even. So that was a very, very big step. Space-time is now fuzzy, so to say. The scale of the areas, which are the elementary units, are more or less a Planck scale to do really physics. Now, going to the period after these two big steps, 91 to 2000, Maja will tell you much more about the period afterwards. I copied first the people who worked with John, or John worked with them, and it's enormous, and the numbers means that the number of publications. So Maja is leading with 21 publications. George has 14 publications, and so on. So unfortunately, Vienna is too far away, so we met at many places. But I still have 6 publications. And the dots means all the others, which have less than 5, which are kind of 25 people. Look, John was so open-minded. I mean, it was really fantastic. We always met and they immediately started discussing this and this and this. And he has always brought new ideas from the geometric side, because I'm coming more from another one. Now, the years here, it's fantastic. These items are more or less the same as the items in the period before, except non-commutativity is always written. Non-commutativity, that was with John, my own work. Extension of electrodynamics. Non-commutative, almost commutative, which means also non-commutative geometry. Non-commutative extension of gravity, non-commutative plane, non-commutative differential calculus, non-commutative Kalitz again. You have heard all this a few minutes ago. Fuzzy space-time means non-commutative, and classical gap, non-commutative geometry, non-commutative Riemannian geometry. So all these items, and also the next, means the same subject which he trained in the 16 years before are now put to the non-commutative framework. So you can imagine the Q-deformed means non-commutative, finite field theory, as I explained, and so on and so forth. And finally, gauge models on non-commutative space. Now, everybody has looked several times to this beautiful book, which appeared first in 1995 and second edition at the turn of the century. And to check complicated things like Morita, equivalence, Hochschild co-cycles, and so on and so forth, which John beautifully collected in this book. To end up, I remember meeting John in Orsay, of course, not so often, by the way, very often in Munich, where he was, so to say, the leader of the group, because Julius West gave us the money, but he was not very often present. and so we met with John and others. Maja was there, and Harald Steinacker, our chairman, was there. And we had a very lively, nice time, especially in Munich. Of course, once in a year in Corfu, once in a year in Bayerischzell, maybe once a year in Vienna. So thank you, John. We like your, I have really memories of many highlights with John. I liked his humor, his jokes. We lost an eminent mathematical physics. I lost a dear friend. We missed you, John. Thank you.
Okay, thanks very much, Harald, for this great overview and great perspective. And in fact, this is obviously also a very good starting point for the whole workshop. And next, also Maja Buric will cover a few other aspects and more recent aspects. I think some personal recollections. Can you hear me, Maja?
Yes, yes. Let me just share my screen. Did I do that? No.
Not yet. We cannot see it. I mean, is she present? Yeah. So I think you should have the bottom where you can share a screen. Do you see the bottom?
This is what I did.
I see you.
Okay, good.
We don't see the
presentation.
But not the presentation, yeah.
I should just, okay, I'm sorry, really. I cannot find it now.
It's below, typically, in the middle.
Yeah. Do you see the green share button? The screen.
Okay, maybe, I know it's not this.
You have to go to the bottom, in the middle.
I have several, I have to go to Zoom, I suppose.
Yes. So I think you should use the access that we sent you in the link.
Except that I don't see it on my screen. Oh, I'm so sorry.
Yeah, no, sure. Yeah. So we also don't see it. I mean, that's yes, it's clear. Sure. When can we do? Yeah.
Okay, share screen.
Okay, very good. It will work hopefully.
Is it there?
No. Did you find the button?
Share.
Yeah, something is happening. Yeah, now it's coming. Okay, great. Yes, we can almost see it now. It's still covered, but yes.
Okay.
Yes, please go ahead. I think it will work. If you close that cover.
That, sorry, and that. And then I should open my presentation.
Yes.
Okay.
Yes.
Okay, so when thinking about how to make tribute to John, I thought maybe tell a couple of jokes and discuss some physics, and that's my plan roughly. So, as you know, John liked to tell jokes and to invent jokes, and one of my favorites, or one which is all over his books and papers, is this one, that non-commutative geometry is pointless, meaning without points, of course. But then I think, or that's what I would say, his interest was also in words in English language and other languages, I suppose, German and French, and those literature, which we know he would always discuss it and go to theaters and so on. So I think one contribution of him is that he introduced the use of fuzzy, that he used this word first and then continued to use it, and it is accepted in the community, like in fuzzy spaces. But then when we talked about fuzzy physics, I think it was a kind of a joke that because of course physics should not be fuzzy, it should be exact and explicit in its prediction. But this expression somehow is also nice to use. So speaking about two pillars, which Harald talked about, I think, or as far as I know, John was one of really few physicists in this generation, in his generation, who had solid background both on general relativity and particle physics. I think for a long time, we had relativists and we have high energy physicists. And the contact between the two was relatively rare, and you couldn't find people who knew both of the things. And as we heard, he worked on a lot of subjects from both sides. But if you look at it, these subjects were in most part connected by differential geometry, because this is the language which he used and which he explored and applied to a great detail, both in gauge theories as first and also in general relativity. John published many papers, and some of them are really very much cited. And his book was read, and of course it had 2 editions, but I think it even inspired more people and explained what non-commutative geometry or differential geometry should be or could be. But I wanted to stress or add to this list of important papers another 2. One is from 87, Conservation Laws and Integrability Conditions for Gravitational and Young-Mills Field Equations. And why do I mention this? It's a kind of explanation and motivation why John believed so much in the non-commutative frame formalism, because in this paper, gravitational equations, or the condition that gravity should be Ricci flat in vacuum, but also Young-Mills field equations are reduced or shown to be equivalent with integrability condition for a specific tensor or Sparling form. This result existed before, but they extrapolated it to gravity and n dimensions and to Young-Mills. It's done with Dubois-Violette. And now this was a kind of motivation or hope that non-commutative frame formalism, although it explains or describes non-commutative spaces with, so to say, no dynamics. There is in this description, there is no field equations and no, in general, no action, no principle of minimal action and so on. But then John always claimed that, okay, sometimes you don't have to have a field equation which are coming from the action. Then sometimes probably you could just have integrability conditions, which Jacobi constraints or Jacobi equations are. So that non-commutative frame formalism still is describes some dynamics. The other paper which I wanted to stress is this one, Kaluza-Klein aspects of non-commutative geometry. And this is sadly the last paper which John put on archive, because he thought that probably this paper wasn't noticed enough. It was done, or the talk was at the conference in Chester in 1988, where he exposed the idea of unification through non-commutative geometry, introducing extra dimensions. So assuming that space consists of the usual commutative space-time tensored with the matrix space, and then that you can split connection in a gauge connection, gravity connection, and the part which would, which is a Higgs field, and then in this way that you can perform Kaluza-Klein unification. And in the paper, it is done on the example of the SU2. Of course, this subject also developed very much, and various particle physics models were also done. Of course, one should mention Julius speaking also of John Madore. As Harald said, John was an important member, one of two or so pillars of the Munich community on non-commutativity. And I had the impression that that somehow he focused also during this stage more from, broadly speaking, mathematics analysis and mathematical development of non-commutative geometry to some applications or to answering some concrete physical questions. And some of the topics, looking at his papers, I think on the gravity side, he mostly worked on still developing geometry, for example, in many details, quantum Euclidean spaces, which he did with Gaetano and Bianca. Then we did a lot of applying non-commutative geometry to gravity, for example, to cosmology, to perturbation, cosmological perturbation. There was a nice example of Grosse geometry, which also would be explained in these terms. So these were the collaborators, roughly speaking, Marco Maceda, his PhD student. And then there is this very important work on field theories on non-commutative spaces and properties of quantized field theories, which was done with probably several people, but most important were Harald and Harold, with their very nice paper. I always admire this paper, I can say, quantization of scalar field on the fuzzy sphere. And then there is a lot of work done in building particle models using the non-commutative geometry and adding fuzzy extra dimensions, where we should add to a list of his collaborators, Paolo Aschieri, and of course, George Zupanos. I would just say a few words on the non-commutative frame formalism, because John thought it was probably his most important achievement, or the biggest thing that he did or contributed. That is his very specific proposal how to build a non-commutative differential geometry. And this he did, I mean, he did everything. And it's mostly described in his book. So it goes from definition of a differential then the differential form and algebra of differential forms, but also it tackles all questions like how to include metric and curvature, how to describe scalar, spinor and gauge fields, etc., etc. So for me, I think it's very good that it's defined very generally, because if you look at the literature, and especially at that time in the 90s, one would assume or discuss one specific algebra, and then for it specifically define differential. So in many cases, it's done still today, example by example, the analysis of geometry of non-commutative spaces. This formalism is made to include also the usual commutative manifolds, but then spaces of matrices, and then also to include operators. Then it describes and it really incorporates geometry of all important non-commutative spaces, like the fuzzy sphere, but also like the Moyal space, that is Heisenberg algebra, and so on. And the idea, which is very important, that it is adjusted for gravity. It's defined in analogy with Cartan's moving frames, and therefore it's, by definition, it describes gravity. Now, what I'm thinking and what I was interested most is perhaps whether it is too constrained. I mean, whether it has too many assumptions to. And just to add, what is the main idea which might survive even if we relax all the, I mean, probably all constraints will be relaxed, and but something certainly will remain, I'm sure, of these ideas, how to approach geometry. So his idea was that we have two structures. One is algebraic and describes the coordinates of the space, meaning the algebra of coordinates with perhaps their spectra, with I don't know, potentially singularities or boundaries or whatever could come. Sometimes people talk of topology, but that's far-fetched, I would say. But then differential geometric structure is given by momentum algebra. And these two sets, moment and coordinates, can be the same in the non-commutative case, but they don't have to be the same. And the important thing is to introduce the frame derivations as commutators, as we usually do. And then the two structures are related through gravity. So gravity comes as a relation via this formula, which gives the tetrad or the Filbine field. And the square of a tetrad is the metric tensor, roughly speaking. And then the structures have to be compatible. They are not a priori compatible. But if we impose compatibility, like we assume that algebras are associative, so we impose Jacobi identities or so, this would give some additional equations which might play the role of the equations of motion. John liked this picture from Irish Cell, where John made a picture of all women. One of the sentences of him, which I thought always relevant and somehow motivated me to work on the subject, is this: algebras are for boys and representations are for men. That means that it's not enough that we just work with the algebras, but the concrete physics comes when we do specific representations, and there things become very non-trivial and sometimes difficult to do, indeed. Okay. We were at many times in different occasions, this occasion and the next one was when we in 2008 made the Irish Cell for John's 70th birthday. Before that, some years before that, we were in Athens at some project which organized by George, and John came to idea to make a limerick for him. then I didn't know what a limerick was. And so the limerick was this one. As there was an old prof from Corfu who used strings to tie up his shoe till a nut from Orsay told him that was okay, but non-commutativity would do. So I thought that perhaps John needed a limerick as well. And here it goes. So there was an old prof from Orsay complained about star products all day, yet a plan made he to frame gravity in a non-commutative way. And this is a fuzzy sphere cake, which Gaetano Fiore ordered in Bayerischzell for this occasion. So I thought we end up perhaps like that. Okay.
Thanks a lot, Maja, for this very personal and very nice contribution. Okay, so I think that is now a nice immediate transition to the current this year's program of the workshop. And Dimitra Karabali will be our first speaker this year. It's also very nice to have you here, since your normal location is very far away. And yeah, so do we have the file? Okay, so the title will be Entanglement Entropy for Integer Quantum Hall Effect in, where was it? In 2 and higher dimensions. Now I will have to pass you the. Do we have a microphone? Yes. I know we have to. Yeah.
Okay.
Higher dimensions. So again, the time is 25 plus 5 minutes.
Okay, so you give me a warning.
I try to give you a
yeah,
warning.
okay, thank you.
Very much, please.
So it's a great pleasure to participate in this conference honoring the Professor Madore. And I would like to say a big thank you to the organizers for putting this together under difficult circumstances that the pandemic inflicted upon all of us. The topic is entanglement entropy in the context of higher dimensional quantum Hall effect. So the standard two-dimensional quantum Hall effect has to do with non-relativistic electrons in a strong magnetic field, which is perpendicular to the surface of the electron of the surface electrons live on. And the hallmark is the Hall conductivity is quantized. So Hall conductivity is defined like that, where this is a current perpendicular to the electric field, which is perpendicular to the magnetic field. And the Hall conductivity is quantized in the units of E²/8. And this nu is the filling fraction, which is integer for integer quantum Hall effect, and has a particular fractional numbers for the fractional quantum Hall effect. Now, this is plays a very central role in condensed matter physics, but it is of wider interest because over the years it has provided a framework for very interesting ideas, such as topological field theories, bulk edge dynamics, and something that is relevant to this conference is it's provided a physical realization for non-commutative geometries and fuzzy spaces. So some very basic things about the quantum Hall effect. We're talking about charged particles on a two-dimensional plane in a strong external magnetic field, so we have to solve the Landau problem. So there are distinct Landau levels, which are separated by energy gap proportional to the magnetic field. Each Landau level is degenerate, and for special gauge, the lowest Landau level wave functions are essentially holomorphic functions up to this exponential factor. Now, the many body problem is interesting. It leads to the so-called quantum Hall droplets. So the degeneracy of each Landau level is lifted if one introduces a confining potential. And because of the exclusion principle, this leads to incompressible droplets. And the low energy excitations of these droplets are essentially boundary fluctuations. These are area preserving boundary fluctuations. So the dynamics lives on the boundary, and it is collectively described by one-dimensional chiral boson given by this action, which is a conformal field theory. Now, in the presence of electromagnetic fluctuations, there is a bulk dynamics and edge dynamics. The bulk dynamics is essentially described by an effective Chern-Simons action, where the overall coefficient is essentially the fill-in fraction. Now, if there is a boundary, we know that this action is not gauge invariant, but there is also an edge action, which is a gauged chiral action, which is also not gauge invariant, so that the two together, the anomaly cancels and the whole action is gauge invariant. Now, this is the effective action and gives the response, provides the response of the system to electromagnetic fluctuations. One can ask also, how does the system respond to stress and strain? In that case, one has to couple the system to gravity, integrate out the fermions. This has been done in 2 dimensions, and one finds that the effective action is given by this series of Chern-Simons terms, where omega is a spin connection, and this index S enumerates the different Landau levels. Okay, now all of these features have been extended to higher dimensions, and the results are quite interesting. So the first attempt to extend the quantum Hall effect on 4 dimensions was done by Hu and Zhang back in 2001, and they formulated on S4 with an SU2 magnetic field. And right after that, in collaboration with Parameswaran Nair, we extended this to arbitrary even dimensions by formulating quantum Hall effect on complex projective spaces. And then other people extended this to different manifolds. But for this talk, I will focus on the CPK case. And there are 2 interesting features that are introduced here. First, of course, is the higher dimensionality, but also the possibility of having both abelian and non-abelian magnetic fields, as I will explain later. Now I will briefly go over our results on effective actions, and then I will talk about the topic of entanglement entropy. So in the presence of a confining potential, again, there are quantum Hall droplets, and now the edge dynamics is described by a generalized Vesumino-Witten-like higher dimensional chiral action. And similarly, in the presence of gauge fluctuations, we found a Chern-Simons-like bulk effective action and a gauge chiral action, so that the full theory is anomaly free. Now, of course, this reduced to the known results in 2 dimensions, but I would like to take a few minutes to highlight the fact that the common origin of all these effective actions is essentially a universal matrix action, which will make the connection between quantum Hall effect and non-commutative field theory a little more transparent. So let's assume that we have quantum Hall effect on some compact space M. Then any Landau level, in particular for simplicity, we take the lowest Landau level, defines an n-dimensional Hilbert space. As I said before, in the presence of confining potential, we have these droplets. And let's say that k states out of n are occupied, then the density matrix for this ground state droplet is of this form. And the most general transformation that preserves the lowest Landau level condition and the number of occupied states are unitary transformations. So under time evolution, this density transforms into that, where U are n by n unitary metrics, and we can think of this matrix U as the collective variable that describes all possible excitations within the lowest Landau level. Now one can write an action for this U, and the action is of this form, where V plays the role of the confining potential, and this leads to the expected evolution equation for a density matrix. And I want to emphasize that at this point, this is a matrix action and has no dependence on the properties on space, of which quantum Hall effect is defined, or abelian or non-abelian nature of fermions. However, we know how to introduce the space-time features in a way which is quite familiar in non-commutative field theories. So what we do is, essentially, we replace the matrices by the corresponding symbols, which are classical functions defined this way. So if we have an operator, we sandwich it with single particle wave functions to find the symbol. We replace products of matrices with star products of symbols, and the trace here by integrating over the corresponding volume element on the space, we define the quantum Hall effect. So I want to argue that this action here is the exact non-commutative bosonic action that describes the dynamics of the lowest Landau level fermions. This was something that was introduced in a two-dimensional context by Sakita, and this is a way to circumvent integration over the fermionic degrees of freedom to find the effective action. Now, there is one more step. We take the large n limit, and in that case, we find that the dynamics is essentially localized on the boundary of the droplet, and this gives the Vesumino-Witten-like chiral edge action. And one do similar things when we have gauge fluctuations. Then one starts with a gauged matrix action, and the corresponding non-commutative field theory, after taking the large n limit, splits into two parts: a bulk action, a Chern-Simons bulk action, a gauge Vesumino-Witten-like edge action. But what is nice in this way of doing it is that the anomaly cancels because gauge invariance is automatically built in. We also we used the notion of Dolbeau index density, and we found an effective action that incorporates both metric and gauge background fluctuations, and this gives this generalizes the so-called when Z terms and the whole viscosity in higher dimensions. Okay, so for the remaining time, I want to focus on the more recent work on the calculation of entanglement entropy for higher dimensional quantum Hall effect and how this compares with the two-dimensional results. And first, let me say a few things, general things about how we define entanglement entropy. So we essentially divide the system into two regions, region D and its complementary, and define the reduced density matrix by taking the trace over the complementary region, and GS is essentially the many-body ground state of the system. In this case, we're talking about an integer quantum Hall effect. So the entanglement entropy is given by this formula, where ρD is the reduced density matrix. And for simplicity here, we're going to use D, we're going to consider a spherically symmetric region of CPK, which satisfies this condition. So just to visualize, in the case of CP1, which is essentially the two-sphere, this region is just a polar cap around the north pole with a latitude angle theta. So this R is tangent theta over 2 via stereographic projection. Now, the lowest Landau level fermion operator can be expanded in this way, where psi's here are the single particle wave functions. And we define local operators by this procedure, A and B. This is integrated over the region D. This is integrated over the complementary region. And lambda is essentially the fermionic density, psi star psi, integrated over the region D. Now the A's and the B's form two independent fermionic algebras, and we can decompose this operator C in terms of A's and B's. So essentially, A dagger is the part, is an operator that creates the part of the wave function which is localized inside D, and B dagger is creation operator that creates the part of the wave function localized outside D. So now if we integrate, if we trace over the B's, so we find the reduced matrix, which is essentially a 2n by 2n matrix in a block diagonal form in terms of these lambdas. And based on that, we find that the entanglement entropy is given by this expression. These lambdas can also be thought as eigenvalues of a two-point correlator, something that was done by Pessel in 2003. So if this is a two-point correlator where Z and Z prime are inside the region D, it's kind of straightforward to see that these lambdas are eigenvalues of these operators. So essentially, in order to calculate the entanglement entropy, we have to know the single particle wave functions and calculate lambda and apply to this formula. Now, for two-dimensional gapped systems, there are general arguments that show that the entropy is essentially proportional to the perimeter of this entangling surface, where C is some non-universal constant. There is a term gamma, which is the so-called topological entanglement entropy, but for integer quantum Hall effect, which is the case I'm looking at, this gamma is 0. And in Rodriguez and Sierra in 2009 calculated this entropy for nu equals 1 in the case of a sphere, which is CP1, and indeed confirmed this formula and calculated this coefficient C. So essentially, I want to repeat this calculation for the higher dimensional quantum Hall effect and see how the entropy looks like. Okay, so for that, I have to give you some rough idea about how we calculate a single particle spectrum in the case of CPK quantum Hall effect. Okay, so complex projective spaces, CPK is a 2K dimensional space, which is locally parameterized by these holomorphic coordinates, but it can also be thought as a coset space. And this kind of group theoretical analysis makes it easier to identify the single particle spectrum. The fact that this factor here is UK, which is U1 cross SUK, shows that we can have both U1 and SUK background magnetic fields, which I alluded to earlier. Also, this shows that the Landau wave functions are essentially functions on SUK plus 1 with particular transformation properties under UK. One can go over this analysis. One finds that there are distinct Landau levels, which are separated by energy gap, like in 2 dimensions. And each Landau level forms an irreducible SUK plus 1 representation, whose degeneracy is easy to calculate, among other things. Okay, so let me be more explicit. So the wave functions can be written as Wigner D functions, where this G hat is an element of SUK plus 1. And one can define left and right transformations. So left transformations on G. These are essentially the magnetic translations that move us from one Landau state to another within the same Landau level. The right transformations, the UK right transformations play the role of gauge transformations. and the rest of them, the cosset ones, play the role of covariant derivatives. Now, how the wave function psi transforms under gauge transformations depends on the choice of background fields. Now we can have a U1 background field whose strength, field strength, is essentially n times omega, where omega is a Kähler-2 form. And in the case of S2, this n is the charge of the magnetic monopole that resides at the center of S2. But we can also have SUK magnetic fields, and the corresponding field strengths, the components of the field strengths are proportional to the components of the curvature, which in the tangent frame basis are essentially the SUK structure constant. So in that sense, we can have also constant SUK background fields. Okay, so the wave function is of this form, where this R has a fixed U1 charge, which is proportional to little n, and this little n eventually is going to be taken to infinity, and this controls the degeneracy of the lowest Landau level, but also it can have some finite SUK representation J tilde. So now I will start with the simplest case, which is the case of only U1 magnetic field, calculate the wave functions, and calculate lambda to find the entropy. Before that, I want to mention also that one can write the Hamiltonian of the system. These R's are R plus and R minus are essentially the holomorphic and anti-holomorphic covariant derivatives. And for the lowest Landau level, this condition applies, which is essentially the holomorphicity condition. Okay, so let's take the U1 magnetic field, which is the simplest case. In that, the lowest Landau level wave functions are essentially the coherent states for CPK, given by that. They form an SUK plus 1 representation of this dimension. And this is the volume element on CPK, which I have normalized to 1. We need that in order to find lambda. Remember, we have to integrate psi star psi over the region D. Okay, so the eigenvalues lambda are given in terms of this formula. For each fixed S, there is a degeneracy factor of this form. So this is the entropy, full entropy, and this HS is the entropy for its mod lambda. Now, it turns out that for large n, this is amenable to a semi-classical analytical calculation. And let me show you the form of lambda. So if one plots lambda versus S, you see that essentially lambda is either 1 when the wave function is localized inside the region D, or 0 if it's localized outside the region D. But there is a transition period, a transition phase here, which is corresponds to the wave functions that are localized on the boundary itself. Now, this kind of pattern for lambda is insensitive to K. It's insensitive to the dimension of CPK. Now, because this is the form for the entropy, you see that if lambda is 1 or 0, entropy is 0. So essentially, what we find is that the H, the entropy per mode, is essentially a Gaussian function, which are sharply peaked around the boundary of the entangled surface. And I don't know if it's clear, but the red is supposed to be a red line here, which is the exact result, and the dotted one, which is a Gaussian approximation. So you see that the Gaussian approximation is extremely good. And that's what allows us to use a semi-classical expansion and find that the entropy has this form, where this is the geometric area of the boundary of the entangling surface. Now, this agrees with the result by Rodriguez and Sierra for K equals 1, But you see that the overall coefficient depends on K. However, if one, instead of the geometric area, chooses to express this in terms of a phase space area, then one gets a universal expression. And let me explain what I mean by that. So the phase space is essentially integral the volume multiplied by the number of degrees of freedom. So if I use this volume, phase space volume, and from that I extract the corresponding phase space area, and I write the entropy in terms of this, then I find this expression where the overall coefficient does not depend on K. So this formula is universal for all CPKs. Okay, so so now let me look at the more complicated case, where is the situation where we introduce also non-abelian magnetic field. Now this is more involved because the lowest Landau level single particle states now form an SUK+1 irreducible representation of this type, where P are U1 indices, L are SUK indices, and there is some condition here. I'm going just to look at the simplest case, and the simplest case is a case where I choose K equals 2. This is a 4-dimensional manifold, CP2, and because of this condition, L is 2. So the smallest possible SU2 representation is a triplet one. There are interesting reasons why the doublet is not allowed, but I won't get into that. So the dimension of this representation is 3. The degeneracy now of the lowest Landau level is more or less at large n what is supposed to be for the abelian case, but it's multiplied with a factor of 3, and this is the 3 that comes from the dimension of this SU2 representation. Now, in this case, there are 3 distinct types of wave functions for the SU2 triplet, and there are 3 corresponding lambdas. The calculation of the normalized wave functions is kind of tedious. I'm not going to write it here. I'll just show you the expressions for lambda. These are related to the corresponding abelian cases, like that. But you see, if I take n going to infinity, these are very simplified. Okay. So if I write down the entropy, the full entropy, it's of this form. But what is important, at large n, it becomes 3 times the case I found for the abelian situation, where I have only an abelian magnetic field. Now, the reason of that is kind of generic. What happens is the degeneracy of the lowest Landau level is essentially the degeneracy I had before for the abelian case, multiplied by the dimension of the SUK representation. And this factor carries over in the definition of the phase space volume and the phase space area. So eventually I find that this formula is universal for any abelian or non-abelian background and any K. Okay, so the obvious question is this true for higher Landau levels? Well, the short answer is that the simple semi-classical expansion that I used so far does not apply. And the reason why is a little bit somewhat interesting. I'll just mention very briefly that if I look at the first excited level now, and I calculate the lambda, if I plot that, I find that more or less the same behavior. Lambda is 1 or 0. However, at the transition phase, it has a kind of a step-like pattern. And this has to do with the fact that the first excited level wave functions have a node. As a result, because of this node, the entropy per mode is not just a simple Gaussian now. It's a kind of a broadened Gaussian, so I cannot use a semi-classical approximation, and I can only calculate the entropy. So the entropy for the first excited level is 1.65 times the lowest, but I do not have an analytic expression for the overall coefficient. Okay, so the same problem applies if I have nu equals 2, and because there is not much time, I will completely skip this, and I will come to the conclusions. So, so I essentially calculated the entanglement entropy for high-dimensional quantum Hall effect on CPK. We found that for nu equals 1, we have a universal formula which is valid for any k, abelian or non-abelian background, assuming that the area is expressed in terms of a phase space area. For higher Landau levels, the simple semi-classical analysis is not valid. So I don't have an analytical expressions for that entropy. And there are two interesting things I want to mention. As now, again, in 2 dimensions, there are general arguments that imply that in the presence of a confining potential, if one has a droplet, and if the boundary of the entangling surface intersects with the edge boundary, then there is an additional log contribution to the entropy, which is of this form. L is the intersection between the entangling surface and the edge boundary, and this C is the central charge of the conformal field theory that lives on the edge. Now, this statement was indeed verified by Estienne and Stefan and Rosenboldt and Krempa in 2018 in the case of a 2-dimensional quantum Hall effect. And very recently, this was extended to 4 dimensions to some version of 4-dimensional quantum Hall effect by these people. Now, regarding this, it is very interesting to analyze what happens in higher dimensions, especially when one has a non-abelian background field, because it is not clear even that the theory that lives on the boundary of the edge is even conformal. So it's not clear what the contribution is to the entropy, the edge contribution is. So that is something that is interesting to look in the future. And the other one, the other question is, how does entanglement entropy change in the presence of gauge and gravitational fluctuations? And this is something that Parameswaran will talk about later, among other things. Okay, thank you.
Thank you very much, Dimitra, for this very clear talk. Are there any questions? First of all, here in Corfu. Please.
Thank you for the nice talk. It's just a very basic question. What do you mean by higher dimensional quantum Hall effect? I mean, in the lab. I mean, the quantum Hall effect is a 2-dimensional thing happening.
In the lab? I never said about lab.
Excuse me?
I never talked about lab. Well, although,
quantum Hall effect is a lab thing.
Yes, although there is a way apparently to simulate 4-dimensional quantum Hall effect in the lab. I can give you the references. I'm not sure exactly how they do it, but they do 4-dimensional quantum Hall effect.
It's difficult to imagine, like.
I'm sorry?
It's difficult to envisage what to actually do. I mean, in 2 dimension, it's you know, the quantum Hall effect. We all know about it. But
yes.
Higher dimensional is just.
Yeah, I mean, as I said, this is an interesting framework to understand a lot of other things, topological field theory. So this is my main motivation for looking
at that. Oh, that's clear and nice. Just wondering about the other.
But as I said, I recently found a number of papers that simulate 4-dimensional quantum Hall effect in the lab.
Thank you.
Okay, any further questions here?
To realize and nowadays, many people try to simulate not exactly this, but some system on quantum computer, and they would say that lab realization of such theory, I think.
Okay, was there one more question, or Peter, maybe short?
Okay. The symbols that you defined in terms of the ground state?
I can't hear you very
You
well.
defined symbols, right, at the beginning. Are the states that you use to define the symbols coherent states? I'm just trying to understand.
I'm sorry, I did not hear your question.
Okay, again. So you define, yeah, now it's working.
If
you
I define
symbols at the
symbols,
beginning, right, in terms of ground states, are these coherent states that you use?
yes,
Okay.
yes.
Okay, do I see any more questions here in Corfu? Does not look like. Are there any questions online? No. Okay, there seem to be no questions online. Okay, so let's thank the speaker again.
Thank you.
And the next speaker is Parameswaran Nair.
Ah, okay. Yeah, where's the pointer? Oh, sorry.
And the title of this talk is Entanglement, Entropy, and Matter Gravity Couplings for Fuzzy Geometry. Please go ahead.
Thank you. It's really an honor to participate and talk in this conference dedicated to John Madore. So I want to thank the organizers for the invitation. Harald, George, I don't know if George is here, Fidele, Costas, everyone. Okay, thank you. What I'm going to talk about is entanglement entropy and matter gravity couplings. And if I okay. The idea is to use the lowest Landau level of a quantum Hall system as a mathematical model for fuzzy spaces, essentially a continuation in philosophy of what Dimitra talked about. In particular, sorry, what am I doing here? Okay. I will be looking more or less at CVK, the complex projective space in K dimensions, where we know that the lowest Landau level wave functions can be defined. These are coherent states, as you mentioned. This leads to some n-dimensional Hilbert space. Observables can be defined in terms of matrices acting on this linear vector space. And then we can define symbols. The algebra of functions on CPK, when n goes to infinity, in that limit, they become a commutative algebra of ordinary functions on CPK. Okay, so this is a paradigm that realizes fuzzy geometry in terms of a fairly physical or fairly easy to understand physical system, which is the Hall effect, the lowest Landau level. So that is the approach that I want to take. As many of you know, I have been struggling with trying to understand some aspects of gravity in this framework. And, you know, the reason for understanding gravity, probably everyone here has worked on gravity on fuzzy spaces, so I don't have to go into details. But the way I want to think about it is the following, that if you take an n-dimensional Hilbert space, and I just give you the space, that by itself does not have so much structure. But when you try to take, you can think of this Hilbert space as coming from quantization of some symplectic structure, some Kähler form, if you like, on a compact space. But the question is, how do we go back? If I take a Kähler form and add an exact form to that, that doesn't change the total number of states in the Hilbert space. And so as an abstract Hilbert space, I get essentially the same structure at the quantum level. So what it indicates is that when you try to go back from the n-dimensional Hilbert space to something classical in the large and limit, there are many ambiguities in it because you're not guaranteed that you're going to get the omega, this canonical structure or symplectic structure you started with. It could be omega plus exact forms. Okay, this ambiguity, this of Largin limits, the fact that there are several Largin limits, I believe that is the genesis of gravity in this context. Okay, and the optimization of that Largin limit should be the Einstein equations. So that's a kind of the operating paradigm behind what I'm saying. But for this talk, I'm going to focus just on two specific aspects of this this problem. The key results I'll be talking about are one is I will look at the entanglement entropy. How does it depend on the degrees of freedom of the space itself, which means gauge fields and spin connection. And I'm going to argue that it's given by a generalized Chern-Simons form. One might ask, okay, that's nice, but why is it interesting? Well, it may be interesting because we know that the extremization of the entanglement entropy can lead to the Einstein equations in vacuum. That's known purely from the gravitational side. No fuzzy input, nothing is needed. If you take the Einstein equations, we can think of it as extremization of the entanglement entropy. So the fact that it is given by a generalized Chern-Simons term is indicative of a Chern-Simons type gravity. So that is sort of the point of interest for this. The second question I want to talk about is interaction of matter fields with background fields. What I will argue is that there is a Chern-Simons form, denoted by S here, depending on gauge connections and spin connections. You shift the gauge connection by the Poincaré-Cartan form for matter. That is the general way to couple matter in this context of fuzzy gravity. Okay. What it implies then is that if you look at the matter part of the action, you'll get the integral of the Lagrangian as we normally do, but it is multiplied by a polynomial in curvatures and field strength tensors. So it's a more generalized form of gravitational coupling for matter. Okay. Again, this may be of some interest because there are situations where such couplings have been used as a possible explanation of dark matter. These are the two main points that I would try to focus on. Okay. Okay, so let's look at the entanglement entropy. We are looking at what is going on here? We are looking at a completely filled Landau level. That's what you need because you're going to look at the full space, the entire Hilbert space H sub n, if you like. And the entanglement entropy is then given by this formula here, sum over lambda S log lambda plus the similar thing with 1 minus lambda, where lambda is the integral over one of the regions. You divide space into two, integrate over one region. Lambda is the integral of that, of the wave function square over one of those regions. Okay, so this is the quantity of interest. And you may recall from the last talk that the Fermion field operator, you can think of it in this expansion like so. This is the lowest level, and we are looking at the fully filled state. Okay, so that's a basic structure. And what I am going to concentrate on is what is the gauge field or gravitational field dependence of this lambda. Okay. How does this depend on lambda? And that, of course, would tell us how the entanglement entropy depends on the background fields. So once again, we have n states in the Hilbert space. We are going to look at a situation where m of them, for example, are filled. So I can define an occupancy matrix, which is an identity matrix m by m. The rest are zeros. That tells me the number of states which are filled. I'm going to look at this quantity. This is not what I'm interested in eventually, but it's an auxiliary quantity that I can use to get the result that I'm interested in. Okay. So the classical function or the symbol corresponding to this is given by this. You take this, multiply by the wave function, sum over, that's what you get. Okay. So this is a standard way to define the symbol. But notice that if I shift this m, the occupancy by 1 unit, I can write u star u as the difference of two of these symbols here. And that's a key. Okay. By doing that, I realized that I can actually estimate this quantity here by calculating this quantity here. Take trace of this occupancy matrix with some arbitrary function or arbitrary matrix A naught. Subtract the same thing for 1 unit of M less, and take the derivative with respect to A naught. That gives me this quantity here. Okay. The idea is this can be calculated without too much trouble. So I can use this formula to get the dependence of the quantity lambda on the gauge and gravitational backgrounds. So how do I do that? It's fairly straightforward and simple. If I just look at U1 fields, let's say omega is the Kähler 2 form, or if you like, the magnetic field for CPK. So this is some multiple, if you like, of the Kähler form on CPK. Then when we add external fields, extra fields, let's say we are adding a U1 field, that's simply like shifting omega to omega plus dA. So I will look at just this abelian case to begin with, which is very simple. And then we can define this quantity here, the trace that I mentioned from the previous slide here, this quantity. So we write this down, but this subscript indicates that this is to be understood as being calculated with the canonical form or symplectic structure, omega plus dA or omega plus F, if you like. Okay. The strategy is to write this back in terms of symbols defined using omega alone, but by modifying A naught to this script A. Okay. And this can be done. And once I have it in this form, then of course I know I can use my old wave functions and so on to define the symbol, write in terms of star products. And again, the leading term, of course, I can even drop the star product. That's what I have. So the whole question is, what is this quantity script A? And that is a problem that is familiar already from classical mechanics. So we don't really need much of quantum mechanics to do at least this one simple case. Recall Moser's lemma in classical mechanics. The idea is if you're given a symplectic structure and a Hamiltonian, I can try to change the symplectic structure and get a different Hamiltonian by doing a coordinate transformation, not a canonical transformation, but a regular coordinate diffeomorphism. And in this way, try to simplify the problem. Okay, so there is a strategy to go from omega to omega plus F via a coordinate transformation. And the price you pay for that is to change the Hamiltonian, which in this case amounts to finding script A in terms of the original A naught. Okay, so the mathematical equations we need are this. I'm going to do a coordinate transformation from V to V minus W. Omega plus F evaluated here should be omega at V, and correspondingly script A would be this. So this strategy can be then used at the level of symplectic potentials. I'm writing the second equation here. So this strategy can be used to calculate this quantity script A. Okay, what does this translate to? It becomes a bunch of equations for this parameter W here, which is the parameter of the coordinate transformation. You don't need to go into the details of that. Basic idea is you just solve them and you find the following equation for A. Okay, so script A with omega to power k starts with A naught, but there are terms which are like so involving the extra potential A, this connection A here, dA occurs here. So in terms of that, you have this series here. Notice that it's going down in powers of omega, so it's naturally defined as a 1 over omega expansion, and that's exactly what you expect because omega, recall, is like an n-fold product of the Kähler form, and we are taking the large n limit. Okay, so 1 over omega is a kind of expansion that we really want. Okay, so once you have that, you can use this expression and write down what is U star U following this formula that I displayed to you earlier, which this formula here, by taking the difference between two values of this symbol that I just calculated, I can get this result over here. So in the presence of a background gauge field other than the omega itself, this quantity U star U is given by the same value at A equal to 0 plus the derivative of some quantity here and further terms here. Okay, what is this quantity Q? That is the leading term that we are interested in. That is in fact a generalized Chern-Simons form. It's explicitly written in this fashion just by summing this series that I showed you here. Okay, so great. Now let me define the generalized Chern-Simons form a little more carefully. The general idea is that if you take an invariant polynomial, which is a kind of thing that occurs in an index density, take for example a symmetrized trace of a product of k factors of f, you take the difference between two different values. Okay, so the polynomial at f prime minus polynomial at f, it's going to be d of something. That q here, whose exterior derivative is this difference, depends on the connection for f prime and the connection for f, and this quantity q is called a generalized Chern-Simons term. If a prime is 0 or a is equal to 0, this is the usual familiar Chern-Simons term. Of course, you might say I can write each of these as d of some Chern-Simons, take the difference. But the point is that there are extra exact terms you would miss if you did that way. This formula actually keeps track of all of that. So this is the quantity that comes up in this expression here. If you do it in the abelian case, take f to the k, take the difference, this is exactly what we find here. Okay, so this calculation I showed you, very elementary calculation along the lines of Moses' lemma, basically tells you that the difference that the extra term you need when you look at this u star u, when you add the gauge field or a in there, is this d of this generalized Chern-Simons form. Okay, and you can now use that formula, integrate, and you get this difference between the lambdas. Okay, so notice that the leading term is this q. There is another term which is subdominant because it is 1 over omega here, and further terms like that. Okay, so this is the key point for us. So once I have the difference of these lambdas, at least for small values, small perturbations, I can calculate the change in the entanglement entropy. It's all going to be obtained from this quantity basically up to some overall coefficients. So the conclusion we can reach from this analysis is that the leading field-dependent correction to the entanglement entropy is this generalized Chern-Simons term that I displayed to you. Okay, it's a fairly simple conclusion, fairly easy to show. Let me just remind you that this Chern-Simons term I'm talking about is familiar from discussions of anomalies in the 1980s. This particular paper, in fact, calculates it for the standard anomalies in 4 dimensions and so on. Okay, this result can be generalized to arbitrary dimensions. I gave you CPK, but with only abelian fields in the problem. But I can add non-abelian gauge fields, gravitational fields, and so on. The bulk part of trace of this occupancy matrix is related to the number of states, because if you take the full trace, its integral of u star u is 1 over the whole space. You're counting all the states, so it's essentially the number of states in the lowest Landau level that determines the structure of this. Now that can be calculated using a Dolbeau index theorem, because recall, these are coherent states obeying a holomorphicity condition. So you want to ask how many holomorphic functions can I write which solve this, which are in the kernel of this d bar operator, and that's the Dolbeau index theorem. It's given in terms of the Todd class and the Chern-Simons character. You can write it in terms of f's and r's and so on, like so. And if I use that, I can again take this polynomial from the Dolbeau index, calculate the generalized Chern-Simons form, like so. There's an explicit formula. I'm not showing you that. But when you do that, you can again calculate the difference between the lambdas, now with a full-fledged non-abelian fields and gravitational backgrounds. And the result is again of the same form. So we can conclude that including gravitational as well as gauge background fields in arbitrary dimensions, the entanglement entropy is given by the generalized Chern-Simons. Okay. Now the point I want to mention is that if you try to extremize the entropy by extremizing the Chern-Simons form, you will be essentially getting Chern-Simons gravity. Okay, so it is leading to the point that if you try to do gravity on a non-commutative space, where of course I'm looking at odd dimensions, not even dimensions, because you have an even dimensional space and time, then that's an extra dimension. In all those spaces, the natural way, the natural theory of gravity that emerges from the fuzzy point of view is a Chern-Simons theory of gravity. Okay, let's go to the second point I want to make, which is I want to consider how matter is coupled. Seems like a fairly simple thing to do. However, there are interesting points one can make about it. There's something unusual about matter coupling. Okay, so let me consider, for example, a matter system whose degrees of freedom I will label by a set of Qs. Lambda is some index which tells you how many of those things there are. And then there are some conjugate variables P. Okay, so this is true for any quantum mechanical system. We need Qs to define the states, but you had to change Qs because there is some dynamics. So there are operators which need to change Qs. Those you call the Ps basically. Okay, and the relevant physical quantity is just the transformation kernel that we all know. It's given by this formula here. And the idea is to think of this Q lambda, which are the coefficients, in a mode expansion of this matrix Q. So the T lambdas are matrices which define a set of mode functions, if you like, in this language of fuzzy geometry. And we can also, so this is what I'm going to use. But let me remind you, there is, just like we define the covariance symbol using the wave functions of the coherent states, we can also define a contravariant symbol, which is a function on the phase space whose matrix elements become the Q, the matrix that you are interested in. Okay, so this is the more like the Toeplitz quantization. Okay, so the strategy here is I'm going to take this expression, convert the Qs and Ps to symbols and the products to star products. So you get, for example, P lambda would look something like this. There is some function phi, which is the analog of this phi here, and then the star product. So this is a contravariant star product that I have to use. Okay. What happens to the transformation kernel, this quantity here? Well, we can just work it out. We all know this is a familiar path integral type description. So what we will end up getting is an expression, a path integral of this form. Phi dot minus h, that these are of course made with star products inside them. So this is some star generalization of the usual PDQ minus HDT, which is the Poincare-Cartan form. So that's what will appear here. There is an integration, but notice that there is a density that appears here. D mu rho together, if I integrate, is going to give me the number of states. So there is a density of states rho that occurs in this problem. Okay. So this expression Z I can write in terms of the Poincare-Cartan form like this. But the key point is the rho. Okay. And as I said before, rho has to come from the Dolbeau index because we are looking at functions which are holomorphic in the kernel of the D bar operator. Therefore, I can use the Dolbeau index theorem, and this index density is going to determine for us what rho is. Okay. So if I take this and write down, for example, the take this as defining the number of states, you can integrate up. This is something we have done in this paper here, and you can write down it in terms of an action, and that is a Chern-Simons like action, like so. So this action here, which is associated to the Chern-Simons form that you can define, right? This index density as D of something, that something is this object here, and that defines the action of interest when I have gauge fields and gravitational backgrounds. Okay. So what happens? Notice that the index density that occurs here is essentially the coefficient of the A naught part, the time part in this expression, because A naught couples to the charge density or the number density. Okay. Therefore, if I take this action and shift this field A by this Poincare-Cartan form, the coefficient appearing in front of script A would be just the rho. And it'll be just right, which means there's a very simple formula I can give at the end. Namely, coupling of matter is given in the following form in this description. You take the effective action that I showed you, namely this guy over here, okay, defined entirely in terms of the Chern-Simons form associated to the Dolbeau index density. You take that, you shift the field by the Poincare-Cartan form for matter, and this path integral then defines for you how matter couples to gravity in this framework. Okay, so if you write it out explicitly, I'm not going into all the gory details here, but if you write it out explicitly as an example, say in 4 dimensions, it takes the following form. So here is my PDQ minus HTT type form, but it's multiplied by a product of field strength tensors and Riemannian curvatures and so on. So this is the coupling that would emerge naturally from the fuzzy point of view. Okay. Notice that the U1 field I have singled out. That's because the U1 field contains the Kähler form, which is essentially needed to give you all the states that you started with. Okay. So this is the basic conclusion, that you have this result here, except I think I have lost something here. Oh yeah. So let me just briefly summarize. So what I have shown you here is that the entanglement entropy for the degrees of freedom that describe space itself, okay, is related to a Chern-Simons form, and therefore there is a point of connection with viewing Einstein equation as an equation of state related to entropy and thermodynamics, which we know already from totally independent arguments on the gravity side. Of course, the kind of gravity that we obtain in this case is a Chern-Simons type gravity, which of course we know coincides with the Einstein gravity in 2+1, but in high dimensions they're different. But what you get is really Chern-Simons gravity. Okay. So this is all within the framework of lowest Landau level as a paradigm for non-commutative version of space. The second result that I showed you on matter coupling is that the Lagrangian for matter is integrated not just with the standard integration measure for space-time, but it's multiplied by a polynomial in curvatures and background field strength tensors. That polynomial is a very specific polynomial given to you by the Dolbeau index that I showed you. Okay. Such modified theories of gravity have been considered before. Here is an example of what goes by the name of FR gravity, but modified with matter in this fashion, and this has been argued to be useful in understanding things like the dark matter puzzle. Okay, so those are the basic results that I have to show you today. Thank you very much for your attention.
Yeah, thank you very much for this interesting talk. Do we have questions here in Corfu? Yeah, please.
So formula you have used for generalizing Chern-Simons looks like transgression formula, yeah?
I'm sorry, I can't hear very well. Could you please repeat?
I just mentioned that formula you have used to generalize Chern-Simons looks like transgression formula. It is
definitely related to transgression formula. No question about it. Yes, indeed.
Yeah, because you haven't mentioned this.
Okay, any more questions here in Corfu? Actually, I will have a question. In fact, this very last slide here, in the last line, so when you add matter, are you suggesting that sort of this last action, which includes Nair scalar, if I understand you right, So is this induced then sort of by as a quantum effect, like in induced gravity or something like that, or how should I understand this?
Yeah, essentially what I'm claiming is that if you couple matter directly to the Hilbert space defining a fuzzy space, and then try to take the Lagrange limit, the coupling you would find is not just matter Lagrangian multiplied by the standard measure of integration, but it's multiplied by a formula like this, a polynomial like this, okay? And that polynomial will contain curvatures. People have looked at such theories with curvature, but what I'm saying is it's both curvature as well as background magnetic fields and things of that sort, okay?
Okay, and when you say matter, do you actually mean something like sort of fields living?
Yeah.
Okay.
Things like scalar fields,
Yeah, okay.
fermions, all that kind of stuff. Real matter fields, yes.
Okay, thanks. Yeah. Now, yes, there is one more question here, Paolo.
Concerning your last point, these curvature terms, extra curvature terms, factors, they are just depending on the scalar curvature, or all kinds of covariant curvature terms?
Yes, all of them. The point is that they are given by looking at this index density. So I'm taking this expression here, which comes from the Todd class and the Chern-Simons character. So this first term here contains all sorts of curvature terms, and not just scalar curvature, not just the Ricci scalar. It will be products of Riemann tensor with itself and so on. Of course, all wedge products, obviously. And then I'm shifting the A from here, so I have to look at the coefficient of A naught in this. That is a coefficient that multiplies the matter Lagrange. Okay, so it is really a product involving all kinds of possible products, but it's a very specific contribution, specific polynomial, because it comes from here. It's not just arbitrary coefficients.
Yes.
Okay.
Thank you.
Yeah.
Okay. Are there any questions online? Okay, there are no questions online. So as suggest we thank you.
Thank you.
And the next talk is online by Kasuki Hasebe. Can you hear me?
Yes, I can hear you. Oh, can you hear me?
Yes. Hello, I can see you. That's good already. Can you hear me? And can you say something, please?
Hi.
Yes. Hi. Okay, we can hear you. Very good.
Yeah,
Yes.
I can hear you. Yes.
Okay, then. Okay, very good. Yes, we can see your slide. Okay, so our next speaker is Kasuki Hasebe, who joins us online with title Quantum Matrix Geometry in the lowest Landau level and higher Landau level. So please go ahead. 25 minutes per slide.
Oh, yeah. First, I'd like to thank organizers for inviting me this nice workshop again. This time, because of pandemic, I cannot attend the conference physically. But next time, I hope I can visit Congo Island again and enjoy the conference with other participants. So please let me start. So today I'll talk about how the non-commuter geometry appears in the context of physics. Maybe I can. Oh, okay. How non-commutative geometry appears in the context of physics, especially in the simple context of physics. For this reason, I will use the Landau model to describe the non-commutative geometry. So Landau model is a very simple model. there is a two-dimensional plane, and on the surface, we put the electron in the strong magnetic field. So I will talk about the realization of fuzzy spheres by using such random models on spheres. Actually, this talk is closely related to the previous talks by Professor Karabali and Professor Nair. So for fuzzy CPN, you can find a series of nice works by Professor Karabali and Professor Nair since 2002. So let me briefly introduce the fuzzy spheres. So this is definition. This relation. These are relations that fuzzy spheres should satisfy. So this is one of the most famous works of Professor Madore. I think I had a chance to talk with him 2 decades ago in Kyoto. We talked about higher dimensional fuzzy spheres, and it was indeed a very wonderful and great experience for me. And several years after the publication of Madore, Professor Grosse and his collaborators introduced the concept of fuzzy force sphere. So fuzzy force sphere is quite similar to the fuzzy two sphere, but the commutation relation is different. So we have to use the whole bracket to define the fuzzy force sphere. So this is the definition of whole bracket. So we take the antisymmetric combination of whole quantity inside the bracket. Okay. The fuzzy three sphere is rather tricky. So again, we use the three bracket, but this three bracket is not the ordinary three bracket. This three bracket is essentially equal to the whole bracket with some operator G5. G5 is essentially the gamma 5 matrix. So let's move on to the 2D case. So this is our system. We put a particle on the surface of two sphere, and at the center of the sphere, we put a monopole. So this is our Hamiltonian. This is covariant derivative. And inside the covariant derivative, we have the SU2 monopole gauge field given by this. Here, I is the integer, which denotes the charge of the magnetic monopole. And this system is SO3 symmetric. The Hamiltonian can be written like this. Here, J are angular momentum operators. And indeed, this represents SU2 Casimir and minus some constant. So by using the group theoretical method, we can easily solve this Hamiltonian. So the result is this. The energy ungiven value is given by this, and the corresponding degeneracy is given by this. And the corresponding eigenfunctions are already known as monopole harmonics, which takes this form. So L was Casimir index of SU2. Usually L starts from 0, but in the case, L starts from I halves. I halves was charge of the monopole. So instead of L, we define N, which starts from 0. And N is regarded as the Landau level index. So this is a picture of the energy levels. So N equals 0 corresponds to the lowest Landau level, and N equals 1 corresponds to the first excited Landau level. So there are a number of degenerate states in each of the Landau levels. The degeneracy is roughly estimated by the charge of the monopole, when the monopole charge is sufficiently large. So next, let us consider the matrix geometry. So this is a simple formula to derive the matrix geometry. So here Y are the multiple harmonics, which are the eigenstates in the Landau levels. So we just sandwich the coordinate with eigenstate, Landau level eigenstates, and derive the matrix elements in each Landau level. So this is a very straightforward procedure and method to derive the matrix geometry. So let's start with a very simplest case. When the monopole charge is 1/2, the degeneracy of the Landau level is given by 2. So therefore, the matrix coordinates is given by 2 by 2 matrix, which is identified as Parameswaran. Okay. So this is an intuitive picture of the fuzzy manifold in this case. So we just have 2 states to constitute the fuzzy 2 sphere. Actually, this is nothing but the Bloch sphere. Okay. And in general, we have a large number of degeneracies in each Landau level. For example, in the lowest Landau level, we have D0 degeneracy. Therefore, the matrix coordinates become D0 times D0 square matrix, which is identified as the SU2 matrix with spin magnitude I1/2. We can play the same game for the first excited Landau level. So you will have the matrix coordinates also given by the SU2 matrix, but the spin magnitude is larger. So in this way, we can show how the fuzzy geometries appear in each Landau levels. So people say, sometimes people say non-conventional geometry appears in the lowest Landau level, but fuzzy sphere geometry can also appear in the higher Landau levels. Okay. So let's move to the 4D case. So this is our system. This we consider the whole sphere, and at the center of the sphere, we put SU2 monopole. So this SU2 monopole is called the Yang monopole. So this is the explicit configuration of the Yang monopole. And here is so-called the Tofuft tensor, which we encounter in the context of instant. Okay? And this is a SU2 spin matrix with spin magnitude I1/2. I1/2 is index of the SU2 monopole charge. The Hamiltonian is given like this. And this system has a SO5 symmetry. Therefore, this Hamiltonian is also given by the SO5 Casimir minus some constant. In the, there are 2 indices in SO5 group, P and Q. And by using a group self-described method, like before, we can easily derive the eigenstate and the corresponding degeneracy, which depends on P and Q, of course. And in this case, in this system, there is a condition for P and Q. The difference P and Q should be equal to the charge of the magnetic monopole. Then, therefore, when Q is fixed, P is automatically determined. We take Q as non-negative integers, which is regarded as Landau levels. So this is, so now the eigenvalue is determined by n. So this is Landau level in the 4D case. And this is quite similar to the 2D case energy eigenvalues. So let's next discuss the corresponding eigenstates. So here is the eigenstate, which is a 4D generalization of the monopole harmonics. called the SU2 monopole harmonics. So this is the eigenstate of the each of the Landau level, and monopole harmonics constitutes the SO5 irreducible representation with some index. So this is the SO4 index, which corresponds to the quantum magnetic number in the original monopole harmonics. Since SO4 is equal to SU2 times SU2, we have two indices, two spin indices, J and K. So because of the SO4 degrees of freedom, the SO5 reduced representation constitutes of many constitute a set of SO4 irreducible representations. So this is a formula with some appropriate J and K. The SO4 representation amounts to the SO5 reduced representation. So let me explain more about this. So this is this figure represents SO5 irreducible representation with fixed P and Q. So the horizontal axis is J, and the vertical axis is K. And therefore, the every field circle represents SO4 irreducible representation. Okay. So a set of these SO4 irreducible representations constitute the SO5 irreducible representation. Okay. So let me give some example. Let's consider the lowest Landau level, which means n equals 1. So in this case, we have only red line. And the SO4 irreducible representations on the red line amount to the lowest Landau level against it. When we consider the first excited Landau level, which corresponds to n equals 2, we have two lines, red line and orange line. And the SO4 irreducible representations on these two lines give rise to the first excited Landau level eigenstates. Okay. So with this in mind, let us consider the matrix geometry of the SO5 Landau model. So let's start with the simplest case, which means the monopole charge is I12. So in this case, we have two field circles on the red line. Each circle has two-fold degeneracy. Therefore, we have four-fold degeneracy in the lowest Landau level. So therefore, the matrix coordinate given by 4x4 matrix, which can be identified as SO5 gamma matrices. Okay. So this is an intuitive picture of this fuzzy cosphere. So this corresponds to, this circle corresponds to the SO4 irreducible representation, and this circle corresponds to the other SO4 irreducible representation. Okay. And as you know, SO5 gamma matrices has the following properties. One is this, and the second one is this. So the SO5 gamma matrices are anti-commutative each other. So when we consider the totally anti-symmetric combination of SO5 gamma matrix, you will have the remaining gamma matrix, which is S5. So actually, SO5 is the minimum representation for the fuzzy sphere. So in general, we have a number of SO4 eigenstates, SO4 irreducible representations on the red line. But matrix coordinate is given by a large size matrix, but it is a kind of generalization of gamma matrices, which is known as a free symmetric representation of the gamma matrices. And they satisfy these constraints, these relations, which is nothing but the relation that the fuzzy force sphere should satisfy. Okay. So we have discussed the fuzzy geometry in the lowest Landau level. Let's move to the higher Landau level matrix geometry. So this is rather tricky. So let's consider the first excited Landau level. So we have two lines on which we have SO4 reduced representations. Let's say this red line corresponds to this fuzzy force sphere-like manifold. And this orange line corresponds to this fuzzy manifold. So each of these is not SO5 symmetry, because the red lines, the SO5, SO4 representations on the red line do not constitute the SO5 reduced representation. The sum of the representations on red line and orange lines constitutes the SO5 reduced representation. So in this picture, I mean, so this is not SO5 symmetric, and this is not SO5 symmetric, but their composite, which is this, is SO5 symmetric. Okay. So similar mechanism happens in even higher Landau levels. Let's consider the second Landau level. We have 3 SO4 lines, and we have 3 fuzzy manifolds. Each of them are not SO5 symmetric, but their composite is SO5 symmetric. So as you know, yeah, this is a kind of onion-like structure. But you must say this does not seem to be SO5 symmetric. So, but this is not the case, because we choose the X5 fifth axis as a quantitative axis to represent the eigenstates. And we can choose any axis as a quantitative axis. We can choose this axis, and the composite manifold is given by this, and the composite manifold may be given by this. These are physically equivalent. So in this sense, this manifold has SO5 symmetry. But again, each shell does not have the SO5 symmetry. So this structure reminds me of the covariant bond of the benzene. As you know, benzene has C6 rotation symmetry, but each of the Kekule structures does not have C6 rotation symmetry. Only the quantum composite of these structures gives some quantum band which has C6 rotation symmetry. And this is a quantum band, so there is no classical counterpart for benzene. So this structure is quite similar to the benzene. So this composite has SO5 symmetry, but each shell does not have SO5 symmetry. So in this sense, this structure is purely quantum mechanical geometry that does not have any classical counterpart. Okay. So let's move to the 3D case. This was proposed by Professor Nair and his collaborator. So the situation is quite similar to the previous random models. So we consider the S3, and at the center of S3, we put SO2 monopole. This configuration is given by this. And this gauge field is quite similar to the Yang's SO2 monopole. By replacing the Tofuft symbol in the Yang monopole with 3-rank response sensor, you will have this configuration. And this Hamiltonian is given by SO4 Casimir minus some constant. So SO4 is equal to SO2 times SO2. So this the index, the energy and eigen's degeneracy are indexed by these two SO2 indices. And the sum of the two SO2 indices essentially gives the Landau level index. But this time we have a new parameter S, which is a difference between J and K. So this is a new parameter that did not exist in the previous Landau models. So consequently, the energy eigenvalues depends on N and S. So this is a picture of the energy band. So N corresponds to the Landau level. So this is a Landau level. This is a Grosse Landau level. But there is some subband structure indexed by S. Okay. So this is a first Landau level, and which also has a subband structure. Next, let us consider the fuzzy geometry in the present case. So let's consider the simplest case. In the simplest case, we have only two subbound in the lowest Landau level. Each subbound has two-hole degeneracy. Therefore, the total degeneracy is 4. And the matrix coordinate is given by 4x4 matrix, which is identified as SO4 gamma matrices. And the SO4 gamma matrices satisfy this relation and also this relation. Please notice we added gamma 5 matrix here. So if we didn't have gamma 5, the SO4 gamma matrices would not satisfy the cross algebra by using 3 brackets. So in general, we have a generalized SO4 gamma matrices, and which satisfies the relation of the fuzzy 3 sphere. So in this way, we can see fuzzy 3 sphere can appear in the context of 3D random model. Okay, so this is so in general we have these subband structures, and so let's take S as some virtual fixed axis and align the fuzzy spheres, fuzzy geometry correspond to these subbands like this. And from 3D fuzzy geometry, we can construct one dimension higher fuzzy geometry, which is nothing but fuzzy S4. I think I don't have time. So there is an interesting relation between 3D model and the 4D model. I will skip this part. And such hierarchy can be generalized to higher dimensions. And in the context of topological insulator, so this structure can be realized. So this is a topological table that classifies the topological insulator. In the S3 class, we have a quantum Hall effect as its 2D entity. And A3 class has topological phases in every even dimension. And A3 class
minutes.
Has topological phases in every odd dimension. Okay, so let me summarize. So I discussed I discussed the matrix geometries of the Landau models on spheres. The Landau model, both Landau level matrix geometries are identified as fuzzy spheres. The higher Landau level matrix geometries yields a pure quantum geometry with no classical counterpart. The 3D Landau model is naturally understood by embedding it into the one-dimensional higher Landau model. So that's all. Thank you so much for your attention.
Thank you very much for a nice talk. So are there any questions first here in Corfu? Yes.
In your picture of the nested spheres that you talked about for SO5, for example, are you able to define things like symbols and star products?
Oh, sorry?
In this example, the SO5 nested matrix geometry,
Yeah.
you know, are you able to define star products and symbols and things like that? Have you thought about it?
Star products?
Yeah.
Yeah, I think. Yeah, I think in principle yes. Yeah, because yeah, this fuzzy manifold also satisfies some kind of algebra. So if you represent such algebra by using the star product, maybe you can express this manifold by using the star product.
Okay. Thank you.
Okay, any more questions here in Corfu? Actually, I have a question or a comment maybe. So in the case of the fuzzy four sphere, so the SO5, the higher Landau levels that you discussed, it seems to me that is exactly what we called sort of generalized fuzzy four spheres. And a few years ago, we wrote a paper with Markus Sperling, and turns out, so they have I think they can be viewed as bundles over the basic fuzzy four sphere with some fuzzy extra dimensions. And they're actually very useful because they can be used to obtain non-trivial symmetry breaking patterns on the fuzzy four sphere. So would you agree with the statement that these higher Landau levels can be viewed as fuzzy bundles over the basic lowest Landau level space?
Yeah, thank you for your comment. And yeah, I'd like to discuss about that with you. But, I have some backup stuff about fuzzy manifold in higher lowest Landau level. So this is a backup. So in the lowest Landau level, the fuzzy manifold is given by the symmetric combination of the gamma matrices. But in higher dimensions, they satisfy these algebras, which defines the fuzzy four sphere. But they are not given by the symmetric combination with the gamma matrices. And also their commutator does not give the SO5 generators, unlike this case. So what, this is what I know about the fuzzy spheres in the higher Landau.
Okay, but I thought all of those should be quantized coadjoint orbits. That was my understanding.
Yeah.
Maybe we'll write some emails later.
Yeah, please.
Thank you. Are there any questions online? No questions online. Okay, so I thank the speaker again.
Thank you so much.
And we have coffee break. I would suggest to make it 25 minutes, or maybe let's meet at 10 before 12 so that we don't get too late for lunch. Okay.
and